In this chapter, we will find out where the name binomial coefficient comes from. As a start, evaluate the coefficients here on the left and write the corresponding values in the structure here on the right. Stop the film and then continue again. Okay, here is the result. Does this remind you of something? If not, have a short thought, stop the film and then continue again. It should remind you of the Pascal triangle, which is used to find the coefficients of the expression a plus b to the power of n expanded. Let us look now at this product here, 4 brackets, each times a plus b, and we see, for example, a1, a2, a3, a4. How do we get that? Well, we have to take one summed from the first bracket times the summed from the second bracket times the summed from the third and times the summed of the fourth bracket. When we're expanding this whole expression, this means we take all possible combinations of these different summands. So how many terms are there with 4 a's? As we see, only one. And this is obvious because the only way to get a term with only a's is if we choose in each of the brackets the a. And there is only one way of doing that. We are choosing 4 times between an a and a b. And to get 4 a's, this means out of the 4 choices, we have to choose 4 times the a. So how many ways are there to choose 4 times the a in 4 choices? Well, exactly 1, or 4 choose 4. By the way, that's the same like choosing in 4 times never a b, so 4 choose 0. So we get there is one possibility of getting 4a, namely 4 choose 4 or 4 choose 0. How many ways are there to get 3a? So for example, a1, a2, a3, b4, or a1, a2, b3, a4, and so on. So this means we're choosing 4 times. How many ways are there that in 3 of the 4 choices we choose an a? Well, 4 choose 3, which is equivalent to 4, and also equivalent to 4 choose 1, which means that we choose in 4 choices only once a b. How many ways are there to get 2a? Well, this means that in 2 of the 4 brackets we have to choose an a. Well, how many possibilities are there? We could take these 2 brackets where we choose the a, or this and this bracket where we choose the a. So actually out of the 4 brackets we have to choose the 2 brackets where we choose the a. So this means 4 choose 2 possibilities, which is equal to 6, and is also the same like choosing twice a b. So again, 4 choose 2. How many ways are there to choose only one a? Well, we have to choose one of the 4 brackets where we choose the a. So we have 4 choose 1, which is equivalent to 4, or also to 4 choose 3, namely choosing 3 times a b. How many ways are there to choose no a? Well, that's exactly one way, namely then when we choose only b's everywhere. So 4 choose 0 for choosing never an a out of the 4 choices, or 4 choose 4 for choosing 4 times the b in the 4 choices. When we look now at a plus b to the power of 4, this is actually the same like up here, except for the a not being anymore a1, but just the a, and here an a, and here an a, and here an a. But in fact, all that we do is still the same like this. We expand it like this, and then we can just put together the same terms. So this is, for example, a to the power of 3 times b, and again a to the power of 3 times b. So we can sum them together to 2 times a to the power of 3b. Well, how many terms a to the power of 3b appear in this a plus b to the power of 4? Well, that's exactly the same question as here. So we see it's 4 choose 3. How many times does the term a squared b squared appear? Well, that's exactly the same question like up here. How many terms are there with 2 a's? And we see it's 4 choose 2. So when we look now at the expansion of the term a plus b to the power of n, how many times does the term a to the power of k, b to the power of n minus k appear in the expansion? Well, from what we have seen before, we understand now that this is n choose k times. And so we see that a plus b to the power of n expanded is this expression here. And we can write that now using the sigma notation as sum of k going from 0 to n of n choose k times a to the power of k times b to the power of n minus k. This is really just a short writing for this expression up here. So what we see now is that in the binomial expansion of a plus b to the power of n, the n choose k is the coefficient of the term akb to the power of n minus k. And that's exactly where this name binomial coefficient comes from. One last remark, as a corollary of the Pascal triangle, we get that n plus 1 choose k plus 1 is n choose k plus n choose k plus 1. Why is this the case? Well, n choose k is, for example, this, then n choose k plus 1 is this, and n plus 1 choose k plus 1 is this here. And we know from building the Pascal triangle that we get this number here by adding its two predecessors above it. Obviously, this is not enough as a proof, but now we can go and prove really that this sum ends up in this binomial coefficient. It is rather simple. Here we just use the definition of the binomial coefficient. Then here we make an algebraic transformation. Next step, we expand by k plus 1 the first quotient and by n minus k the second quotient here. And now k plus 1 times k factorial is just k plus 1 factorial times the n minus k factorial. So we have this denominator here, and here we have k plus 1 factorial as here, and n minus k times n minus k minus 1 factorial is just n minus k factorial. So I have 2 times the same denominator, so I can write it as just as one fraction, adding to 2 denominators, and then summing it up. We get n plus 1 times n factorial, which is n plus 1 factorial. And in the end, we just get, again, using the definition of the binomial coefficient, n plus 1 choose k plus 1. That's it.